Welcome to Symbol Emergence and the Solutions to Any Task. My name is Michael Bennett. I am a PhD student at the ANU. Quick overview of this paper. I'll begin by defining intent, then I'll formalize an arbitrary task and its solutions, then argue that an agent which always constructs what I call an intentional solution would qualify as artificial general intelligence. I'll then explain how natural language may emerge and be acquired by such an agent, conferring the ability to model the intent of other individuals laboring under similar compulsions because an abstract symbol system and the solution to a task, as we define it, are one and the same. So, how might we define intent? First, I might state my intent generally. For example, a parent may intend to keep their child alive and healthy. This is an overall long-term goal, a constraint they try to satisfy. On the other hand, there is the intent of a specific context, the rationale behind a decision. This is a sub-goal which is constructed by assuming someone pursues some overall goal in a particular situation. The overall goal and the situation together provide context for a rationale. For example, I might observe the parent of an addict confiscating their drugs, and infer from that the parent intends to prevent the addict from overdosing. I do this by first assuming the parent is compelled by an attachment to the addict, a general intent. And then from this very general intent, together with the observed behavior, I construct a rationale for the parent's behavior, a sub-goal in service of which the drugs were confiscated. This is a message abducted from both the observed behavior and an overall intent that I assume the parent held. Just as I can construct a rationale for the decisions of another individual, I can attempt to communicate a rationale for my own decisions. Humans communicating a rationale usually concern themselves only with the specific sub-goals rather than any general overall goals a human might have. And this is because we often share those overall, very general goals, such as familial attachment or the desire to acquire status and so on. To fully explain my rationale, I must not only state the immediate sub-goal in service of which the decision was made, but to explain it I need a chain of steps indicating how that goal was to be served, whether it was successful or not. However, possession of an explanation is not the ability to communicate it. The meaning of programming language is exact, specified in the physical arrangement of transistors, or, if we look at clocks and the gears and pulleys, or in dominoes even. But humans communicate in terms of loosely defined abstractions, not this dyadic one-to-one deterministic thing. We tailor our explanations to express what is important both to ourselves and those to whom we are speaking, given a particular context. Such language must be interpreted. It's a means of encoding, transmitting, and decoding more complex information. So the question is, what is this complex information? What is the interpreter? And how might we build it? Before continuing, I just want to clarify the notion of symbols a bit. So we might define a symbol as a dyadic relationship between a sign and a thing to which it refers. This is called a referent. This makes sense in the context of a programming language where an exact definition is necessary. Each instruction has only one interpretation. We know how to implement such a thing using hardware, so we'll call such dyadic symbol systems physically implementable languages. However, dyadic symbols are not abstractions akin to symbols in natural language, and those abstract symbols have a much less clear nature. Symbols determine about what we may reason, and so one symbol system may facilitate success in a given task better than another. And as to the nature of messages, we'll borrow a little from Peircean semiosis, which, rather than defining things dyadically, defines a symbol as a triadic relationship between a sign and a referent and an interpretant, which links the two and determines their effect upon the interpreter, that is, the agent observing or interacting with the symbol. I aim to clarify exactly what this interpretant is and how it may be constructed. Recall that in the earlier example, the rationale of the behavior of a hypothetical drug addict's parent was obtained by assuming some overall intent or goal. The family member's behavior was a signal, and the assumed overall intent served to decode that signal into a message, a rationale. This is a subgoal. So understanding natural language is not just about clustering sensory-motor stimuli, but imbuing stimuli with significance in terms of a goal. To formalize this type of meaning, we require a goal, and it should be constructed in one of these physically implementable languages, so that we can actually compute it. For simplicity, we'll need to describe a goal as a statement which has a binary truth value, true of a subset of possible hardware or sensory-motor system states, and false of others. Hard-coding such a goal is impractical. It needs to be learned by interacting with the world, so we assume cognition to be embodied, situated, and extending into the environment, which would facilitate experimentation. If a goal is to be learned, then the question remains, which goal? Which is most plausible? What is most likely to generalize? And here lies the connection to AGI. No doubt, a few of you have heard of AIXI, a theoretical artificial general intelligence which employs Occam's razor to decide which model of the world is most plausible. Solomon-Off induction formalizes Occam's razor by measuring the complexity of a program by its Kolmogorov complexity, the smallest self-extracting archive, which in this case reconstructs the agent's past experiences of the world. As a result, AIXI learns the most accurate predictive models possible given what it has already observed of the world. To decide which goal is most plausible, we can follow a similar line of inquiry to formalize Occam's razor in terms of statements rather than programs, using the weakness of a statement instead of its length. To do this, we need to first define an arbitrary task without which a goal would be meaningless. I'll briefly describe this formalization. First, we need a finite set of binary variables. Then we require a set of every complete or partial assignment of values to those variables. These are sequences representing hardware or sensory-motor system states. We also need a subset of these sequences, which is the set of all goal-satisfying states. And then we have another subset, which we'll call the set of all situations. This is all the initial states, which are sequences in which the agent needs to try and make a decision to satisfy the goal. And so for each situation in this set, there exists an acceptable goal-satisfying supersequence in the set of all goal-satisfying states. The process by which a decision is evaluated is as follows. First, the agent finds itself in a situation. Then, the agent selects a supersequence of that situation and writes it to memory. We'll call this supersequence a response. If that supersequence is in the set of all goal-satisfying states, then the agent will have succeeded at the task to an acceptable degree or with some acceptable probability. To reiterate, the state which is given to the agent is a situation, and the supersequence which the agent chooses is a response. For those familiar with AIXI, a situation may contain past memories and so is functionally similar to a history. The distinction between the situation and response is that the situation provides context for a decision, while a response is the result of it. But context alone does not tell us which response is correct. We still need a goal, a statement whose truth value determines correctness. Such a statement is necessary to determine whether any given response, given a situation, is correct, and sufficient to reconstruct all the goal-satisfying states given the set of all situations. We'll name any such statement a solution to the task. To distinguish between possible solutions, we draw upon the notion of intentional and extensional definitions found in the philosophy of language. For example, the extensional definition of a game of chess is the enumeration of every possible game of chess, which is legal. And the intentional definition is the rules of chess. However, this seems a little incomplete. Any statement could be a rule. In what way are the constraints that we call rules any different from simply listing every legitimate game? So I would posit that what we choose to call the rules of any given game intuitively tend to be the weakest, most general individual rules necessary to verify whether a given example of a game is legal and sufficient from which to abduct every possible legal game. Conversely, enumerating all valid games is just a means of describing chess in the strongest, most specific rules possible, although we wouldn't call these rules. The rules of chess describe the task how to play chess. But there's no reason we can't extend this notion of rules from merely how to play X to an arbitrary task, such as how to play X such that your chance of winning is maximized. To reiterate, a rule is just a statement written in a physically implementable language. A statement is a solution if it's necessary and sufficient to reconstruct the set of all goal-satisfying states from the set of all situations. For every statement, there exists a set of hardware states of which it is true, and the greater the cardinality of this set, the weaker the statement. To say one statement is weaker than another is to say it's true of more hardware states. So, given a physically implementable language of any practical use, there will exist a means of joining two or more statements to form one stronger statement, this would be something like and of joining two or more statements to form one weaker statement, for example, or. In either case, the resulting statement may be longer, so weakening doesn't necessarily imply compression. Just as statements can be joined, a statement can be split into shorter, separate statements by deleting a connective. At every split, we could measure the weakness of the resulting statements, then the weakness of the statements that result from the dissection of those, and so on, to measure the overall weakness of a statement's constituent parts. Whether a solution is overall an overall solution or just a sub-goal, which could provide a rationale for a decision, depends on the scope of the task we're considering. So it's arbitrary. The point here is to illustrate how two solutions might be equivalent, but formed of very different components. In this regard, we'll propose two extremes of the domain of solutions for a given task. So first is the extensional solution. This is formed of the strongest, most specific rules necessary and sufficient from which to abduct all goal-satisfying states from the set of all situations. It does not state what responses share in common. Instead, it specifies each goal-satisfying response separately. It is unique, given a task in a language. On the other end of this spectrum is the intentional solution, formed of the weakest, least specific rules necessary and sufficient to abduct all goal-satisfying states from the set of all situations. It stipulates what these goal-satisfying states tend to share in common. It defines what is necessary to verify correctness, but it doesn't need to state what the responses, the exact responses themselves. And it may not be unique. There may be many such solutions. Earlier, we defined intent as a goal. And it is certainly not the case that humans prefer to describe goals by enumerating every example of success. We try to describe what successes of a certain type share in common. We generalize. We will subsequently name an agent that always constructs intentional solutions an intentional agent, and one that always constructs extensional solutions a mimic. Given a task and an appropriate choice of physically implementable language, if we bundle each solution with a SAT solver and the set of situations, then for each solution we have a self-extracting archive that reconstructs the set of all goal-satisfying states. We will name this a solution archive. The length of such a self-extracting archive varies only with the length of the solution it employs, the set of situations being uncompressed and the solver being the same for all solutions. And for each task, there exists a unique value given a language, the length of the smallest solution archive. Note that this is not the Kolmogorov complexity of the set of goal-satisfying states, because we are not allowing the set of situations to be compressed, and we are only considering SAT solvers as decoders. However, we can interpret Occam's razor as stating that an explanation should not assert anything more specific than absolutely necessary, and a stronger statement is more specific in that it asserts more than a weaker statement and is false in more hardware states than any weaker statement. This is what is important about Occam's razor, why it works. It minimizes the possibility that a resulting statement is false. In contrast, the extensional solution is made up of statements, each of which is as specific as possible. It's false in each one is false in all hardware states but one, because each describes a unique goal-satisfying state as part of the extensional solution, minimizing the plausibility of the solution's constituent parts. Among those shortest solution archives we were talking about, there would exist an intentional solution because a longer statement using strengthening connectives is less plausible than a shorter one, and at least one intensional solution must employ no more weakening connectives than strictly necessary, which would minimize its length without losing any necessary information. If we modified AIXI to consider only solution archives as models of the world, then it would be likely to find an intensional solution, because one must exist among the shortest solution archives it prefers. Any intensional solution will suffice, not merely the shortest, though. Just as AIXI maximizes reward across all computable environments, an intensional agent is one that attempts to maximize accuracy across all possible tasks. This is to say that in a specific task, an agent possessed of a more specific inductive bias may outperform an intentional agent, but may not match an intentional agent in general across all tasks. If we accept Shillette's definition of intelligence as the ability to generalize, then these intensional and extensional solutions represent the product of its extremes. If, given a task, we choose a physically implementable language of such limited expressiveness that only a finite number of solutions exist, then an intensional solution is computable by iterating through all possible solutions and comparing them. Of course, this only transfers the difficulty involved in constructing an AGI from the design of an AGI to the design of this physically implementable language. Learning typically relies upon an ostensive definition, that is, a small set of examples, in this case goal-satisfying states, serving to illustrate what correctness is. Using an ostensive definition, an agent could construct a statement which is necessary and sufficient to reconstruct those examples of goal-satisfying sequences from a set of given situations. However, whether this solves the task as a whole, the task as a whole being what those examples are of, depends on how this statement is constructed. The mimic makes no attempt to generalize. It will eventually encounter a situation for which it knows no response. In contrast, an intentional agent may construct the rules of the task as a whole. We say that an ostensive definition is sufficient if the ostensive intentional solutions it implies are necessary and sufficient to reconstruct all goal-satisfying states for the task as a whole from the set of all situations. If an ostensive definition is not sufficient, then the resulting intentional solutions will still be rules, but not to this task. It's not sufficient to capture the rules of this task. This means an intentional agent would achieve optimal predictive accuracy for a task if given a sufficient ostensive definition, not just any ostensive definition. Among the possible solutions to a sufficient ostensive definition, some will be more intentional than extensional, meaning they generalize better. If one can generalize more effectively, then one learns faster. Every example added to the ostensive definition would convey a greater increase in predictive accuracy for the intentional agent than any agent that only constructs solutions closer to mimicry. All that said, greater intelligence does not always serve a purpose. Given a uniform distribution of goal-satisfying responses, the intentional and extensional solutions would both need to enumerate all goal-satisfying states, meaning no generalization would be possible. Also, while an intentional agent may be faced with computationally expensive abduction every time it needs to construct a response, a mimic's response would require minimal computation. It's akin to rote learning or human intuition, the ability to form a correct response without understanding what makes it correct. Fitting a function to a set of points may have more in common with mimicry than intent, which would explain why commonly employed machine learning methods require so much data yet struggle to generalize. Perhaps to combine generalizability with computational efficiency, the best approach is to seek both extensional and intentional solutions, the former to construct a heuristic. Biological organisms are not usually given an ostensive definition. Instead, we are compelled by primitives of cognition, such as hunger and pain, or the familial attachment mentioned in the introduction. These are for all practical purposes objective functions. By selecting those responses which resulted in the most favorable reward, we seem to construct ostensive definitions which we can then reason about and decompose into rules, identifying what members of an ostensive definition share in common. Now that we've understood solutions, we can return to examining language. A solution is playing the role of an interpretant. It determines the effect of stimuli, that is a sign or a referent, upon an agent. Stimuli relevant to success in a task can then be perceived as a signal the agent must interpret. So a solution, together with a situation, allows signals to be decoded. Conversely, any response which results in the agent taking an observable action could be perceived as emitting a signal, and so a solution also facilitates the transmission of signals. What is communicated is a rationale. The scope of a task is arbitrary, so we can split a solution into shorter statements, each one of which is the interpretant of an abstract symbol or a particular subtask. The boundaries of a symbol are therefore fluid, just like in natural language. A solution could be seen as both an abstract symbol as itself and as a learned symbol system constructed specifically to efficiently describe what is important in a task. Human language is made up of general abstractions, and so an extensional solution would not be much use in capturing this system. For the same reason, we cannot hard-code meaning of natural language in a dyadic programming language. A more intentional solution would result in a much more flexible decoder because it could split up into generally applicable abstract symbols. Communication requires signals be imbued with similar meaning by both a sender and a receiver. In order to construct compatible symbol systems, as we've described, two agents must construct approximately the same intensional solution so that stimuli is imbued with similar meaning by both. This explains the emergence of normativity. Such a solution should account for the existence of other agents operating under similar compulsions. Otherwise, an agent would never be compelled to respond to a situation by transmitting a signal. And so it must be learned in an environment where such other agents are present. If agents noticeably affect each other's ability to satisfy their compulsions, then solutions will imbue the observable behavior of other agents with meaning. And if cooperation is advantageous, then repeated interaction will produce conventions that facilitate complex signaling. I'll briefly illustrate what might be involved in encoding and decoding signals now. So to decode, we first construct an intensional solution or something close to it. We then observe another agent responding to a situation and apply our own solution to construct a rationale for their behavior. If we succeed in this, we interpret what a signal means, what the immediate sub-goals are that are being pursued by the other agent. We know what they want, what they desire, what they mean. A signal of this form is not limited to spoken words, but any behavior, as in normal human interaction. The more plausible the sub-goals we can identify, given an assumed overall intent, the more confident we can be that we've understood. However, if my solution provides no valid rationale for the observed behavior, or it's very implausible rationale, then the other agent's overall solution might be very different from my own. And in this case, I need to hypothesize some modified intensional solutions that do permit a plausible rationale. And in doing so, perhaps learn a more general solution from a different or more intelligent or more experienced agent. To transmit is to affect change in the sensory motor state of another individual. One may convey or request information pertaining to sub-goals in order to cooperate, or perhaps deceive in order to obtain some competitive advantage. In either case, the intentional agent is treating the other individual as part of the environment to be affected, then choosing a response which it predicts will satisfy its goals to some acceptable degree or probability. To encode, we first need to decode the behavior of others to predict their immediate sub-goals, what they want, what they will understand. And then we ask how might they respond to our potential responses, and choose a response that we predict will result in them responding favorably to in terms of what we want. So to iterate why task splitting and merging is so important, I'll give an example. Assume we have a more intentional kind of agent, which is a dog in a community of dogs. Its compulsions specify a general overall task we might call being a dog. And each day a human rings a bell when food is available. And each day the agent observes the sound of the bell, and then the running of the other dogs to the location where the food is placed, and then the food itself. The construction of a solution to an ostensive definition of the subtask we might call satisfy hunger will associate the bell, the behavior of the other dogs, and the sight of food, all with the satisfaction of the hunger compulsion, and so imbue them with meaning and become part of symbols associated with the satisfaction of hunger. Now consider another subtask. We might call it avoid pain. A larger dog growling may be associated with pain after a few bad experiences, and this is a message that conveys hostile intent. It becomes part of symbols associated with pain and fear. But having learned what a growl conveys, the agent may transmit this signal in order to obtain food claimed by a smaller dog, combining the rules of two subtasks in order to satisfy the goal of one. The joining and splitting of symbols facilitates this generalization, and projecting one's own solution, one's own experience onto others is what allows the transmission of the intent. So one last comparison before I conclude. This audience is probably familiar with alignment problems in AI safety. So what I've essentially put forward is that communication in humans amounts to an alignment problem. I wonder if there might be some interesting avenues of future work there. And as to future work, I am working on experiments to test these ideas. As it stands, I've constructed an agent that learns intentional solutions to binary arithmetic and other trivial tasks. But tests pertaining to more meaningful benchmarks are in the works, but they require a much more expressive, physically implementable language. All right. Thank you for listening.